So let's look at the common approach to do quantitative analysis on the execution time. We'll first construct the processor behavior model, and we'll use model to find worst case starting processor state for each basic block. And we will measure the execution time of the blocks from these states. And we'll use these times as upper bounds on the time of each basic block. And then we formulate a integer linear programming to find the maximal sum of these bounds along any program path. So there are several steps we're gonna go through, and I will introduce that. But again, if you reflect, if you look at this part, really we're doing both of these two things. One is the processor behavior analysis, where we will put the basic block into the processor, let them execute, or manually to find out, to build a model of the processor, and then doing simulation, then to understand the execution time of these basic blocks. And then we're going to use the program path, i.e. the control flow graph, to understand the possible paths, the longest path, and then together with the information from the basic block, then we can infer the execution time. So let's look at this example. We have a simple program segment here. We have two variables, n is 10, q is 0. You can think about n is the upper bound for the loop, q is the loop iteration variable, and we have a while loop. The condition is q is less than n, and in the loop iteration, we're going to increment q by 1 every time. Once this loop is done, we will assign r to q. So given this program, even though we have only a few lines, if we want to build these basic blocks, we're talking about 4 basic blocks. Why 4 basic blocks? Because first 2 lines of code, they will be in 1 basic block, because these two are sequence of instructions. They will be executed together. While loop, this line is a separate basic block, and this q++ is another basic block. And finally, this q equal to r, this is the 4th basic block. That's why you see we have 4 boxes here, B1, B2, B3, and B4, representing these 4 basic blocks. And the instructions are also listed as part of the basic block. The basic blocks, you have, when the program starts, you enter the first basic block. After that's finished, you will enter the second basic block. And we have true and false conditions. If it's true, then we're going to execute B3, this basic block. If the condition is false, we're going to branch out to execute B4 basic block, and then the program ends here. And because it's a while loop, so we also have a arrow pointing back to itself. It's not showing up correctly here. Anyway, so this is the control flow diagram. Once we have this control flow diagram, we also use a few numbers to represent the execution behavior. X1 or xi is the number of times a basic block is executed. So x1 here is number of times this B1 is executed. X2 is for basic blocks 2, and then X3, X4 are for the other basic blocks, respectively. D of J is number of times an edge is executed. So we also have these symbols D1, D2, D3, D4. That's the kind of the while loop. Should be here. And we have D5 and D6. So these are the edges and how many times these edges are executed. Okay. Let's see. Yep. So if we label these execution blocks and number of times execution blocks and edges are executed, then we can measure the upper bound on the time taken by a basic block. So C of I measures the upper bound on time taken by BI. So this one, CI is, for example, C1 is the upper bound on time taken by this B1 basic block. Now, to understand or to get this upper bound, we of course need to execute this small segment, this basic block, on the processor, either on a real processor or using some simulation tool on the simulator to get the number of cycles or in seconds, how much time does this basic block takes. Okay? And we may not get the exact number, but we can estimate the upper bound for this basic block. Essentially, how in a worst case scenario, how long this basic block will take to execute. So that's the meaning of CI. When we represent CI, well, the execution time of B1 as C1, and if we know this basic block is executed for X1 times, then C1 times X1, that will be the total time this basic block is executed. Right? Make sense? Because C1 is the time that this first basic block takes, and X1 is number of times this basic block is executed. So that gives us the product of these two, give us the total execution time of this basic block. Similarly, we can estimate the time taken by this basic block. That will be C2 times this X2. And this will be C3 times X3 and C4 times X4. So altogether, the execution time of these four blocks will be this accumulated sum. Now, this is what we want to calculate, but to calculate this, we have to make sure that these variables subject to constraints. The first constraints here is X1 equals D1 equals D2. Let's see, why is that? When we go into D1, that's from the starting program start, the number of times this path or this edge is taken is definitely the same number of times this B1, this basic block is executed. Otherwise, the basic block is not a basic block. The definition of the basic block is it has one entry point ingress, and also it has only one egress path. And that's exactly the number of times this first basic block is executed. Okay. The second constraint is D1 equal to 1. And that's our assumption that we want to execute the whole program just once. Okay, so D1 is 1. So that implies this D2 is 1, X1 is 1. And then X2 equals to D2 plus D4. So why is that? X2 is the execution time, or the number of times basic block 2 is executed. The only way this basic block 2 is executed is when we go into this B2 through D2, or we self loop through this D4. So that's how many times we go back to B2 from this part. So D2 plus D4 is X2. And when we get to this while loop, depends on the condition, we will either increment Q or branch to here. So the number of times that B2 is executed, X2, equals to D5 plus D3. So that's the constraint, because you only have these two possible branches. And then X3, D3, D4 equals to 10. That's, so what we see here is this X3 is going to be, this B3 is going to be executed 10 times. And then D4 is going to be 10 times because of the while loop. And we have X4 equals D5 and D6. So same thing. So this is one basic block. There's no other possible branches. So the number of times this edge is taken is going to be the same number of times this basic block is executed, the same as D6. So these are the constraints. And then really what we're trying to do is, while we have these variables under such set of constraints, what will be the maximal value of this accumulated product? Okay. In this example, we know these numbers, 10, etc. In some cases, we may not know the exact number, but this problem definition gives us a way to calculate the maximal execution time, which corresponds to the worst case execution time. So as we mentioned earlier, we define this model, which is a integer linear programming problem. And we want to find integer values, xi, that maximize the sum subject to these constraints. This is an NP-hard problem. To solve this is not always easy, but there are good software tools, ILP programming software that can help you to solve this problem, to give you the maximal value of this accumulated product given a set of constraints. And if you have a longer, more complex function to analyze, you can imagine that these conditions will be more, but the way to solve this is the same, using integer linear programming. Okay, so we saw that analysis tool earlier using linear integer programming. In some cases, we can look at individual statements to try and find if there's any dependencies. In this function, altitude PID run, it has several lines of code. First one is to calculate the error. By the way, this is part of the drone control autopilot code from an earlier project. Then use the error, we will try to estimate the desired climb by using this statement. And then we have two if statements. If desired climb is less than minus climb max, and we will assign that to the lower bound. The second if statement is to check the desired climb. If it is greater than climb the upper bound, then we will assign the value to the upper bound. So how many feasible paths? The reason we say here is feasible instead of possible is that, even though you may think there are several possible paths because you have multiple if statement, but if you look at closer the conditions for these two if statement, we can see that for any given value of the desired climb, it will only take one of those. So only one of these statements will be executed. If it is lower than this climb max, this lower bound value will be assigned, then this if statement, this condition will not be true. So this line of code will not be executed. And similarly, if this desired climb is greater than, is not less than, then we're going to be checking this. So in this case, for these two basic blocks, remember, even though this is one line of code, we still think this is one basic block. So we have one basic block, the other one basic block here. Then this adds an additional constraint in the form of x of I plus x of j less than 1. Because you can't have both of them being executed. You can only execute one of them, just because the way these bounds are checked using these two if statements. Okay, it seems doing this control flow graph model and using integer linear programming, we can possibly analyze the worst case execution time. But if you have a task with two parts, A and B, composed in sequence, let's say for this particular task, we have A as the first half of the task in the sequence and B as the second half of it. And then what is the worst case execution time when we have this WCETA and WCETB? Can we just add them together to get the worst case execution time of the overall task?
Not necessarily.
Mm-hmm. Can you maybe explain why or give example?
So the worst case in task A may not be always connected to the worst case of task B. Means like maybe there is some variable and it has some value, and if that value causes the worst case in A, but it does not cause the worst case in B, so maybe it's not together to get two worst cases at the same time. So yeah, that's why I think that it may not be always true.
Yeah, very good. That's right. So it's not always true. You cannot simply compose the worst case execution time because there could be dependencies through the environment. Chances are there's two parts. The first part A will change certain environment variables, which this part B depends upon. In that case, it will not necessarily give the same case B get to the worst case execution time. So it's not always going to be composable.